Welcome back to Nature of Code in Rust and GGEZ. It's been a while, but I'm back into recording these. Now, I'm only going to be doing them once every little while because I've got some other projects I'm also working on at the same time, but I am currently committed to doing as many of these as I can because I do want to learn the lessons of them. So looking where we last left off, we're on exercise 2.6. So the formula for drag also included surface area. Can you create a simulation of boxes falling into water with a drag force dependent on the length of the side hitting the water? Well, let's take a look at the last thing we did, which was this exercise 2.5. So let's run this. And there's a few things that I sort of want to change here before we can start moving. First of all, I want to have everything start at the same location at the top so we can see the differences as everything falls. So let's head into the main library, and right here where we're creating our movers for the Y, I'm just going to go ahead and make these 50.0. Okay, so first change there. Now we need to make these boxes. So let's head back into mover here. And what I want to do is, instead of a radius, we're going to have a width and a height. For our width, let's make this equal to twice the mass. So we'd have to have something that's like easier to see. So we're going to take a mass and multiply it by 2. Now for our height, it sounds like height isn't going to be part of this equation. So I'm just going to make it be just a static 10, and that should be fine. So instead of radius here, we're going to have a width and a height. All right, now that does cause some problems. Like for example, in draw here, we have to actually create a rectangle and draw it. So let's first create our bounds as it is. So the bounds is equal to a rect. This starts with our position. So self.location.x, y, and then our self.width, self.height. And then we can convert this or switch out from a circle to a rectangle. We're still going to have a draw mode. And it's going to be a fill, just like before. The bounds is going to be that bounds rectangle that we just created. And then color. Let's just make this white, just like those circles. Coming down here, okay, so check edges. Hitting the ground, so to make sure that it actually doesn't do anything, beyond bounce. Let's see, we want to... What is this doing? Is checking like, okay, self.location y plus self., so this should be self.height is greater than screen height. Okay, so if it's greater than that, self.location y equals screen height minus self.height. Oh, and then self.velocity dot y times equals -1. Okay, so we reverse and like it bounce back up. Okay, so that should be fine. Is inside the zone. So self.location y plus self.height. Okay, so that's how we know if we're inside the zone. And apply drag. Okay, so this is going to be new and different, but I'm gonna worry about this in a little bit. We have a warning here. Our warning is saying that we have an inconsistent structure. So we have location with height, color, velocity and acceleration. So it's saying it doesn't like the fact that they're out of order. So what I can do is hit Control dot, or I think Command dot maybe, and Rust Analyzer is gonna go ahead and fix that for us. And then we don't need that radius anymore. All right, no more warnings in here. We do have one in zone, but it's that same out of order. So we're gonna fix that in the same way. All right, let's go ahead and run this and see what it looks like. Okay, so things are looking good. Now they're still dropping based upon is that the mass? Oh no, just based upon the size. Just based upon the size. But that's not necessarily helpful here. So what's happening here? We're using let's see. If we take a look at our, because we need to now make sure we're factoring in the that let's see, what is it? The frontal area of the object, which is right here. So it's this A. So what I want to do is sort of like redo this section here and keep this in mind. So I'm going to keep this over here to the right so I can see it. And we're going to just redo this really quickly. So this is our force, and it's going to be equal to -1/2, but 1/2 is just a constant. So we can just have that be 1, and 1 times anything is whatever. So it doesn't mean anything. The negative is important, but we'll get to that in a little bit. Okay, so P is the density of the liquid. Again, we can just imagine it's 1, so that's fine here. Velocity squared. Okay, so we can get that. So let our speed is equal to self.velocity, get the magnitude, and then we can square that. So, and the idea is that we're going to take velocity squared and then just multiply all of these things. So we can actually do this all together. So let our drag is going to be equal to self.velocity magnitude, and then take this number and we want to get the power I of 2, so raise it to the second power. Okay, then we want to multiply this by A. So A is the frontal area of the object. So let's take just self.width. Okay. Then we have the C. The C is the coefficient of drag. If you remember, we have that inside of the zone. So times the zone dot coefficient of drag. And then we have this V. This refers to the velocity unit vector. Okay, so we're going to normalize it and then point in the right direction. And if we take a look at here, it's basically the opposite of V. Okay, so that's fine. So this gives us an F32 number, which we can now take our velocity. We can clone it. And normalize it. So let's do mood. We want a self.velocity. Okay, so we'll actually call this the drag force. Equals self.velocity. Now I want to clone this. So let's try clone. See if that works or if it yells at us. Then we want to normalize it, so we can actually just do this right here. So we're going to normalize it. So clone and normalize. Oh, normalize doesn't return anything. So never mind. We are just going to normalize. Next. So take our drag force, normalize it. We are also going to reverse it. Drag force dot reverse. And then we can multiply it by this drag. So drag force times equals to drag. And then we can add this to our acceleration. So acceleration equals the drag force. All right. Now you're saying using clone on something that has the copy type. So we don't really need to do this. It's going to go ahead and copy it. So let's go ahead and run this and just sort of see what happens and see if there's any numbers that we need to. Yes, we definitely need to play around with some numbers. So those disappeared. Now, out of a little bit of practice, because I sort of like looked at this ahead of time just to refamiliarize myself, it didn't disappear down, it disappeared up. So what's going on is there's the drag force is so high that it hit the water. The water is like cement for this, but instead of like being cement, it's now like a trampoline, and it bounced off of it. So we need to make sure that this coefficient of drag is an appropriate number. So we're going to come back up here to where we create our water, and this is way too high. So I think we're going to try, let's try like something like this. A very, very small number. And that passes through. We do notice maybe that's not enough drag. So let's take 1, 0 off. So notice that these boxes with the really wide, they kind of bounced when they hit. Like they hit the water, they bounce kind of a little bit up and then they go through, whereas the thinner boxes, they just pass straight on through the water line and continue their momentum down. I think that's really cool to see because that's exactly what we see in real life. If something really wide is thrown into water, it can actually bounce because as it's moving pretty fast, the water sort of tightens up, looks like concrete. It hits that, splats, and then sinks. So that's what we've got. We're able to now tie in our drag to the width of the box hitting the water. Thank you so much for watching, and I'll see you in the next video. Bye.